All right, let's begin the third act of our course today, and that is actually getting down to the nitty-gritty of assembly, opening up our practice program, and seeing how it translates to x86 assembly. So let's go ahead and make a new project. We'll just call it, let's see, we'll just call it practice Ghidra project. That works. And we'll go ahead and add, I'm going to add actually two executables here. So here's our compiled practice program, completely compiled. And then I'm also going to add the 64-bit version, which I compiled with VS Code. And I'll show you the differences of that after we get through walking through the assembly of our program. But you can see I've compiled it up here for 64-bit as opposed to 32-bit. And it'll be quite a bit different looking than the one we made with GCC. But for now, let's focus on our original practice program. We'll load it in, and we'll double click to open it up. It's going to ask us if we would like to analyze it. We certainly would. That will have the disassembler go through it and perform all these options. I am going to turn off dwarf. You can usually leave almost all of these by default on, the default ones that they have for the standards. But I do know that this version of Ghidra will throw an error if I have that dwarf running. It won't crash anything, but it's just annoying to have to deal with. So I'm going to leave that off and let it analyze. We can see the status bar down here, and we can see stuff start shifting around as a disassembler does its thing and starts trying to analyze all of the parts of our program. So that was a pretty quick analysis time. Let's just do, I did do a quick kind of overview of Ghidra in the Solitaire video as well. But just to touch on some of the basics, we have the sections of our program up here, and you remember some of these from the cheat sheet. So here's our, oops, there we go. Here's our .text section, which has all of our instructions here. .data section, which has a lot of our static data that's been defined already. For example, right here, we see there's a piece of data called global, which is our global variable that we defined right at the top of our file right here. And we can also see in Ghidra how it has references. And like I said in the Solitaire video, you'll notice that some of these references, these cross-references as they're referred to, will have a W, which means they are written to at that address. And some of them will have an R, which means they're read from at that address. So in this one, we can see that our global integer variable here is read from twice, and that is in both of those are in QuickMass at two different places. If you remember, we can check QuickMass to confirm this. We use it once, or I should say we use it twice in the same line right here. So first we print the actual value of global, and then we shift it one, and those are both times that global is read. Here's our .bss section. Most of this is going to be added by the compiler itself, and you can see up here there's a ton of other sections that we didn't discuss in the cheat sheet, but a lot of common ones like resource. If you watch the Solitaire video, we talk extensively about the resource section and how we manipulated the images in that section there, relocations, some debug sections, etc., etc. Below that, we have our symbol tree, which has a list of all of the functions that are included in our executable, imports, exports, classes, namespaces, all of the different pieces of our executable. And then we have our data type manager, which we'll play with in just a little bit, showing us all the data types that are included in this program. A lot of them are from the built-in standard library here too. And of course, in the middle, we're going to have our disassembler view. That's going to have all of the assembly language there. And cool feature of Ghidra is this nice decompiler view, I should say, which has a kind of C pseudocode of what Ghidra is assuming is going on in this assembly code over here. It's not always fully accurate, but it will get you 80% of the way there most of the time. It's basically taking this assembly language, tracing through it, and trying to reconstruct the high-level C code from that. And as we discussed in the Solitaire video, if you have trouble seeing any of these fields, you can click on this guy right here. Looks like a little table. And you can stretch out any of these fields that might be cut off, or maybe you want to make them a little shorter so you can see the comments at the end there. I'm going to leave that alone for now. I think this looks pretty good size-wise, and I think it's been saved from the last time I was working in Ghidra, so hopefully you all can see this just fine. So let's start by finding our main function. Now there are a couple ways to do this when you first start up Ghidra, and the easiest way probably is to just search for the word main. But there are actually quite a few functions in the executable that have that word in them. For the record, this is the one we would want, is the one with just the one underscore. And we can tell that that is our main function that we're looking for because, and let me try to extend this out just a little bit so you can see here. We can see that this one has 3 parameters passed in, argc, argv, and env. If you're not familiar, what those are is for every C program, when you write your main function, even if you don't, for example, like here, we didn't define those 3 parameters, those are always passed into your main function. argc is the number of command line arguments that have been passed into your program. argv is a character pointer, so an array of character pointers or an array of strings that has those command line arguments. And then this other character pointer is env, which has all of your environment variables there. If you want a quick demo of what that looks like, let's go ahead and just do a quick C file. We'll just call it test.c, and we'll actually write out that same function signature here. So we have a character pointer argv, or actually I'm going to actually do it like this to make it more explicit, and then a character pointer environment. Oops. Let's get this out of the way. And let's go ahead and for int I equal to 0, I less than argc, I plus plus, and then we're going to go ahead and printf, and we'll do a string for every argument that's in argv there, and then we'll just return. So basically I just wanted to print out, and oops, I do need to include my standard IO header, and that'll allow us to print out our command line arguments. So let's go ahead and compile this, make sure we did that right. Oops, let's use exe, not test that out. We'll get rid of that. There we go. So let's go ahead and run test.exe. Windows Defender's crying a little bit, trying to make sure everything's okay. And you can see we've just printed one argument, and that is the path to our executable. So bear in mind that every time you write a C program, the first command line argument, no matter what, is going to be the path to whatever program is running. Now, if I have additional command line arguments like different flags or test this, you can see that those have been added. Oops, except let's go ahead and add a new line here to make that a little clearer. We'll recompile. Try again. So you can see that each of those arguments, we now have 4, are going to be passed in. And if you do something like putting quotes around one of those arguments, it will be treated instead of 2 separate arguments as 1. So now we have 3, argc is 3, and we have 3 command line arguments there. So just wanted to quickly touch on what that function signature is all about. So that's one way to find it, is just straight up look for main. Another way is you can go up here to your exports. Every executable is going to export a function that's going to be called when we enter into it. For GCC, it will oftentimes make this main CRT startup function, which will simply do a jump to another function. And this is basically, if we look at it's probably easier to see through the decompiled view. This is basically, let me blow this up a little bit. 1 second. Okay, apologies. I forgot with Ghidra, you can adjust the listing size in the middle here, but a little bit more difficult to, from the GUI at least, to adjust the font here. Hopefully you can see it okay. But this T main CRT startup is basically a prologue in our executable to kind of get our environment set up and make sure our program has everything it needs to run. There's a lot of stuff inserted by the compiler right here. But if you go all the way down here, at the very end, after we gather our environment variables and other variables and parameters here, we can see a call to main with argc, argv, and this guy, which was assigned to the environment variables there. However you find it, let's go ahead and go to our main function here. And we'll do a little bit of orientation to the view in the listing here. So at the start of every function, you're going to see this nice big function banner. It's going to show you the return value type, which is an integer for main. The calling convention, which we see is cdecl, as we discussed. And then the name of the function, of course, which was main. And then all the parameters. And you can see right below that, it'll actually show you the layout on the stack when main is called, which has a return address, argt, argv, and the environment variables on the stack locations. And then we see now we're subtracting from the stack to get all of our local variables here, which are simply named local blah, 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 blah. That number afterwards is the offset from the base pointer, by the way. Let's move down, or actually let's touch on, we already touched on it a little bit, but you can see here cross references to main. So, or I'm sorry, these are cross references to the variables themselves. You could also see cross references to the function, like right here. And you can click on those cross references to travel back and forth. And then from left to right here, we have the virtual address of each instruction. And then right here, we're actually seeing the hexadecimal representation of each instruction. So the move instruction on disk looks something like, if I go to hex here, 89, oops, it's good if I have numlock on, 89, E5, 83, E4. Looks like something like that in binary. And we would see that if you search for that binary in our little XXD output we talked about. You can actually take these binary codes, by the way, like this one right here, copy it, and I'll include this site in the resources, but there's a nice site called Diffuse that has a nice x86 and x64 assembler and disassembler, where you can put an assembly language and actually assemble it, or you can disassemble any hex string, such as this. So let's go ahead and disassemble, and we can see that it gives us the exact same instruction that we see in Ghidra. Pretty cool. All right, so we see the hex version of that, and then we see, of course, the actual instruction and assembly, and then the operands over here. Sometimes you'll see some comments or helpful hints from Ghidra about what it thinks, certain things should be labeled as, or what it points to, references, such like that. We'll get to the listing in more detail in just a moment. Just to wrap up the little tutorial here, to Ghidra here's our decompiler view. We already talked about this is kind of a high level reconstruction, and it has a nice feature where if I click, let's say over here to this jump, sometimes it takes a minute. If I click over here to this jump, there we go, or this compare or move or whatever, you can see that it will adjust the highlight in the listing accordingly. You can also do things like right click, highlight, or secondary highlight, and it will highlight one variable in that listing. Same thing over here. We can also use, just like we did in the debugger, we can label everything. So if we know what this local variable is actually going to be referenced by, we can go to edit label and label it something like blah. I think that's good enough for a quick overview. Again, if you haven't seen my Roller Coaster Tycoon Solitaire videos, we use Ghidra quite a bit in those, and we explore several different features. And as we go along through our assembly here, we'll use several more as we go through our code and start defining things and helping Ghidra understand what's going on, since we're lucky enough to have access to the original high-level code. For now, let's start at the very top, and we're going to do the exact same thing that we did with the high-level C program, and that is walk through everything, but this time in assembly. And you're going to see there's some stark differences when we do so. So let's go ahead and I'll go ahead and pull this just a little bit, maybe right there for now, because we're mostly going to be focused on this middle section right here. So we'll try to remove a few of those distractions. And let's go ahead and get to VS Code and just get where we can follow along as we walk through the program. So again, we know that we start out by calling print function header. Let's just start with tracing through that step right there. To start off, note that we have a little prologue here once main starts that does all of the things we already discussed with the stack. So we're going to push the current base pointer onto the stack. We're going to move ESP into the base pointer registry there. The only piece we may not have seen yet is this AND ESP with 7Fs followed by 0. If we look at that in binary, that's all of these bits set except for the last 4, the lowest 4. Why are we doing that? Well, to keep it at a very explain like I'm 5 level, it's to make sure that we're aligned to a 16-byte boundary. This is something that computers tend to like for efficiency, so the compiler will make sure that the addresses are along a 16-byte boundary. So for example, if our, let's just take this address here, 401E-F8. That is not divisible directly by 16, and this is in hex, keep in mind, 16. There's a remainder of 8. But if we take that address, 401EF8, and we AND it with that value right there, we'll clear out those 4 bits, and now we get a nice division by 16 without a remainder. So that's why we see that at the start of our program here in the main function. Now this next piece we are familiar with. This is adjusting that stack to make room for all these local variables. But you'll notice again that it's a little bit more than what we need for our local variables. This is what, if we go to right click and where's my convert? There we go. I hadn't clicked in the right place. In decimal, this is 112 bytes. Whereas in reality, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 local variables of size 4 plus 1 of size 1. So that ends up being what? 13 times 4 plus 1. Something like 53 bytes is really what we need. But it's giving us a little extra space there for any other stack growth that might happen within the course of the function. You may also be curious about this double underscore main. This is inserted by the compiler as well. Anytime you see a double underscore like this usually means that it's something internal that the compiler is doing for optimization or to make sure things are running. So I'm not going to dwell too much on this function because it just does some setup for us here. What we're really interested in is what happens next as we get ready to call our print function header function. Right here, you can see that we're passing in the variable at the address here in the data section at this address. And if we look in the disassembly window, we can see that it's picked out at least the first letter of that string, but it looks like Ghidra doesn't quite understand that this is not just an array of characters, but a full string. We can have it more explicitly define this by changing this to data string, and it will complete that to main. If we go back, we can now see that this has been translated over to main. It's got the same address there, and it's even updated our decompiler view. Very handy feature of Ghidra there. So nothing surprising here. We are moving the string main onto the stack on ESP. And then, of course, we're calling our print function header. Again, we see a lot of the same things we saw in the main function. The difference being that this one has a lot more cross-references because every function will call this. You're probably also wondering why we have 2 local variables here. What's going on is when we call this print function header, we're passing in the function name as parameter. But even though that's going to be in print function header stack frame as a parameter passed in, we still need to move it onto the stack again in order to have it placed correctly for printf. What I mean by that is the reason we have 2 locals here is because we're going to take our parameter, which let's go ahead and relabel this as function name since we know the parameter name, and we're going to move that off of the current place on the stack as a parameter using EBP to reference it, and move it into the EAX register. We're then going to take that and move it back onto the stack, but this time you can notice we're adding it above the current ESP. So we're getting it to a place that's a little farther up the stack so that it can be passed in as a parameter to printf here in a moment. So let's call this, oops, not that. I want to label this guy here. Let's call that local function name. And then, of course, this is going to be our defined string that has the formatted running string there. So we can just call that running or something, run string. That works. So that's why you may sometimes see these phantom local variables that you may not recognize, but the compiler, who generally knows what it's doing, is adding these and accounting for them so that everything can be placed on the stack correctly, and all these sub functions that are called within this function can be called successfully. So there's not much else to this function. We pass in the parameter, we pass in that run string to printf. There's nop in the wild there. And then leave, as we talked about a little earlier, I believe, is a special instruction that completes a few things. So it basically undoes all three instructions right here. It moves the base pointer back into ESP, and then it pops the base pointer off the stack. So when we return here, remember return also does some stuff under the hood. It's going to basically just set our EIP, the instruction pointer, to the line right after that function was called. So right back here is going to be where we pick up in main. Hopefully that all makes sense, and that was a nice little function to start with because it's pretty straightforward. Now let's keep going and take a look at some of our other functions. So next, we are well aware that we have 3 integers, local variables that are initialized right here. So we can technically go back here and rename these accordingly, or label them as X, and then this was Y, oops, and then this was Z. But we do have to be a little bit careful because sometimes, or I'm sorry, this was not Z, this was result. We do have to be careful though because sometimes compilers will reuse local variables even if we didn't intend to reuse them for different things. The compiler might say, oh, I'm going to use this local variable in the stack to push something else once I'm done with this other value. So you do have to be careful with labeling to make sure everything's being used in the right context. So we got down to here, X is 5, Y is 7, result is 0. Then we're moving another 0 into another local variable. Well, what's that? Let's go back to the high level code here. That is going to be this integer I right here. And I'll show you how you can take a look and tell that. I mean, you can look at that decompiler and it will tell you right away. But let's go ahead and just, well, let's not label it yet. Let's just take a look at what happens next. So very next thing that happens after we move 0 into that local variable is we make a jump. So this is an unconditional jump. We will always jump to this location right here, this address, and we can click on that, double click, and it will take us down to that section. It's comparing whatever was put into that, or whatever variable that 0 was put into up here. It's comparing that value to 9, and if it's less than or equal to 9, it's going to make a jump somewhere else. This pattern here is very indicative of a loop, and sure enough, if we look at our code, whether it's in the decompiler view or not, we can see that array size, which is 10, is compared with I, and so it makes sense that we're doing a check to see if I is less than or equal to 9. If it is, we're going to break out of that loop, or sorry, if it's less than or equal to 9, we're going to go right back up here, and we're going to perform this loop. If it's not, we're just going to keep moving on, and that means we've broken out of the loop. And you can see when I highlight there, Ghidra does a nice job of demonstrating that in the decompiled view on the right there. So let's go ahead, now that we have done that little bit of analysis, let's go ahead and label this as I. Makes it nice and easy. So again, we know exactly what's going on here. We are basically initializing our array with values 1 through 10. Now, one thing we didn't see right away is where that array actually is initialized, like where this line comes into play. We did a initialize to, give me an array of this size. So let's see what's going on there. So this section right here within the loop is where the magic of initializing that array is happening. If we look here, let's just trace through the loop here real quick. We move I into EAX. Again, this is a nice little trick that saves us a couple instructions by using load effective address. Instead of loading an address right here, we're basically using LEA as a sort of shorthand for this addition. So we could have done move I into EAX, and then add EAX1 or increment EAX, and then move EAX into EDX. That would have been 2 instructions at least. Instead, what the compiler's done to optimize that, and it's used LEA, and it has simply included EAX plus 1 in here instead of an actual address, and it's taken the result of that and stored it in EDX. So hopefully you followed that. We're basically just saving ourselves one instruction by using LEA as opposed to an increment or add and then a move to EDX. So again, all this is doing is loading the value I plus 1 into EDX. So that's going to, the value that's in EDX is going to become what gets placed in our array. Now next, we move I back into EAX right here, and then we use it as a sort of index times 4 hex, which is also 4 in decimal, plus the ESP, plus this value 0x34, and then we move the value that we want to place in our array to that location. So what this is doing is it's using I as the index, and it's multiplying it by 4 because 4 bytes are the size of the integer, and it's using that to index into the array, which is based at wherever ESP plus 0x34 is located. And then this last line is simply just updating, adding 1 to I. So that can be hard to follow just looking at the disassembly. Let's hop over to the debugger real quick, and let's see what that looks like in real time. So right here we are stopped at the very top of the loop. We are currently loading I, which is located at ESP plus 6C, this guy right here, into EAX. So EAX is now 0. We then load I plus 1 into EDX right here. That should be 1. And then we move I back into EAX, which there's not going to be a change there because I hasn't changed. And now here's where the magic happens. We're going to move the value in EDX, which again is the value we want to put in our array. We're going to move it to ESP plus 34 plus I times 4. And again, that means, the translation of that is that our array is going to be based at ESP plus hex 34, which would be, in this case, DFF8D4, which is right here. And since I is 0, this 0 times 4 is 0. And so we're just at the base of the array, and so we're going to place our value in EDX right there. So let's watch that happen down here. So I hate that I should have frozen that first, but we can look, what was it? 8D4, right there. Yeah, okay, so it did take me right there. So there is the first element of our array. So let's go through one more time. And now we should see, now that I is 1, we're now going to move it to ESP plus 34, which is the base of our array, plus I times 4. So 1 times 4, which is 4. Again, remember, the whole I times 4 thing is just to account for the fact that each integer is 4 bytes in length. And so when we want to store something one integer away from something else on the stack, we have to remember to multiply by 4 to make room for it. So let's see where that takes us. It takes us to D8 right here. So we should see 2 placed into that location. And sure enough, oops, it moved a little bit. So 0, what was it? D8 right up here. We see we're slowly building up the array right in the stack. Now the significance of this is that, let's see, where are we now? Right here, we're at 4. Yeah, so let me just go ahead and get through the rest of this loop. I'll set a breakpoint here so we could skip ahead, remove this breakpoint. All right, so the loop is finished. Now if we look at the stack at, where did I leave off? 8F8, right here. If we look at the stack, our whole array has been initialized right there in the stack, which it should be because that array is a local variable. So the reason I'm spending so much time on this is because, if you remember, we were looking at this instruction earlier, which was subbing 0x70 from ESP, and we're wondering, okay, we only have, I can't remember what it was, it's something like 53 bytes of local variables that we had to account for. So why is it allocating so much memory on the stack? Well, this is one reason that we didn't necessarily take into account when we first talked about that, is in our main function, we have an array of 10 integers, which are going to be 4 bytes each. So that's another 40 bytes we need to account for. So all that to say that the compiler is being very smart when it allocates whatever number of bytes it allocates on the stack. And we should usually listen to it when it's asking for that amount of space. There are other factors at play here too that we didn't talk about, such as, again, like with the print function header, we may have extra local variables that we have to account for. We may have to account for 16-byte alignment, etc., etc. So that number should make sense in the context of everything we'll be doing with the stack in this function. All right, I belabored that point enough. Let's keep moving on. We hopefully understand better this loop here and how we're initializing that array right on the stack. All right, back in our high-level code, the next thing that happens is we define our character array right here. I'm a string look at me, followed by a new line, and then we calculate string size. So let's go examine what that looks like in our disassembly. And you'll notice that when we get to this point right after that loop to initialize ARR was completed, we get to a bunch of move commands that look a little odd. They're moving these large hex numbers to local variable slots on the stack. So what's going on here? Well, the disassembler is interpreting that as hex data, but if we right click and convert to character sequence, you'll notice a pretty obvious pattern going on as we go through all of these. I don't know if actually, can I do a bulk here? All right, I just ended up doing that manually, but if somebody does know in Ghidra, if you can select multiple sequences and then convert them all at once, please let me know in the comments. Please and thank you. But for now, we can look here and we can see that the contents here are a backwards version of our character array, which is I'm a string, look at me, including the new line and the null byte at the end of the array. Why is it backwards? Well, this has to do with endianness, which I've talked about, and I probably all of my other videos, at least in one point in time in the video. But basically, endianness comes down to what type of machine you're running on, whether it's little endian or big endian oriented. In a big endian oriented system, the most significant bit will be displayed first from left to right, and a little endian, the least significant bit, will be placed left to right when you're reading it. This is a little endian system, and so we're seeing the string loaded backwards because the most significant bit is over here. So that's why we're seeing this show up as backwards in our listing here. And you'll notice that these are getting loaded into different local variables, so different slots on the stack. And we'll come back to that in just a little bit when we start using that character array. For now, let's go move down to where we're calculating the size of that character array. And we can see the decompiler picked up on our little shorthand loop right here. So we know that local 67, if we go back to our loop here, is going to be probably the address, the base address of the string array. And then what was the other one? Local 18 is probably going to end up being our string size variable. Let's see if we can confirm that. Otherwise, we can do so by looking up here. So if we look up here, we'll see that local 67 is indeed the start of our array. We can see the first characters being loaded in right there. So we'll call that string. And then we know that local 18 is going to be our string size. We could also look down here and see how that's being initialized. They're moving 0 into string size and then moving 0 into string size again. Sometimes these the way the compiler duplicates instructions doesn't make much sense to us, but the reason it's doing that is because we set it to 0 here, and then we reset it to 0 once we get into our for loop. So it interpreted that as 2 instructions. And then of course we start our for loop here. By the way, one feature I neglected to mention earlier was the function graph window that you can get in Ghidra, which makes some of these loops easier to take a look at visually. So let's zoom in here. You can see that the function graph view basically just makes a visual representation of all the assembly we looked through so far. I don't know if there's a way that I can actually, fill these out a little bit more. I guess not. I was hoping I could maybe, oh, here we go. So if I pull this out, will that do what I'm looking for? Or maybe if I go here, operands, labels, let's see what that looks like. There we go. Okay, so adjusting it the same way we do in the listing, we can kind of see a little bit more of the instructions there. And what's nice about this view, like I said, is it's really good at pulling out loops and showing you kind of the logic of the loops, as well as conditionals like this one. So this one's saying that if jump less than or equal to, or I should say, if this comparison is true, so if this I variable is less than or equal to 9, then we're going to jump to this loop right here. That's the green, is if true. If it's false, we're going to move on down here. And that was back when we were iterating through our integer array. So here we are back in our loop where we're calculating the string size. And right here, we start the loop, we add 1 to string size, we load, let's see if we can move down here, or right here is where I want to be. We load the value, the base of string into EDX. We then take string size and push it into EAX. We add the two together. So we're basically using the string size as an index, just as we saw in our high-level code right here. We then move the value that is at that address of string plus string size into EAX, and then we test the lower bits of that. So if you remember, this testing of a register against itself is equivalent to ANDing the register with itself. So if that is 0, that means the value in that register is also 0. So as long as it's not 0, if it's not 0, we're going to jump back into this loop. We're going to increment string size. If it is 0, we're going to move on with our lives right here. So I just wanted to point out the graph feature in Ghidra because it is extremely useful. If you've used IDA, another disassembler, and they do have an IDA free version, by the way. If you use that, IDA tends to default to showing you the graph view rather than the listing view, and I can see why, because for a lot of people they enjoy the visual aspect of that. All right, so already we are halfway through our main function, at least on paper it looks like that, but in reality we have a ton of functions that we still need to go through in the meat of our main function. So let's go there next, and the next thing we'll do is call quickmaths and also print the result after we get it back. When we do so, we of course are going to load the local variable y into EAX and then move that onto the stack, load x, move that onto the stack, and then call quickmaths. So again, we basically just push those onto the stack in a different way than using the push command. We've just moved them into an area on the stack there. So we could actually call these, and you'll see them get reused. This is one of the things I was saying about being careful about labeling. This local 7c and local 80 are probably just local variables designated for passing parameters to other functions. So we'll just say, we'll label this param2, and we'll call, oops, why did the rename fail? Oh, maybe because param is, I'll just call it par2. Param might be a special word that's reserved, so we'll call this param1. So we're moving x into the first parameter view, y into the second parameter, and then we call quickmaths. So I don't think there's anything too surprising up here. Let's move right to the meat of the function. We've already talked through the prologue and what's going on with the stack here. So the first thing we do is we call the print header function, and again that just consists of moving quickmaths into that stack and calling the function. Next, we're going to start getting into all that arithmetic that we do in quickmaths. So let me pull up that in the high-level code so we can follow along. And this is going to be one of the first interesting points in the assembly here, because we're going to be doing our first dynamic allocation with this memory allocation right here. So first things first, we know that 3 gets moved into local variable A. We'll go ahead and label that as A. And then you'll notice we move 4 into this local 2C, which again is a local variable that looks like it's dedicated to holding our parameters. So let's go ahead and rename that to par1. And we're sending that to memory alloc or malloc. Why the variable 4, or why the value 4? If you remember, we pass in the size of an integer, which in this case is 4 bytes. So the return value from malloc, like many return values, is going to be stored in EAX after that function call. So we take that return value, we move it to local 14. That's equivalent to our B variable right here. So let's go ahead and rename that to B. And then we compare B to 0. That's the comparison right here to see if it's null. And if it is 0, we print, uh-oh, no memory left. And then we move 0 into our return value, and we straight up return from there. Otherwise, we move on with our lives. And if we go back to our high-level code here, the next thing we do is we set B's value to 5, we initialize M, and then we go through all of our addition, subtraction, multiplication, division operations here. So B, we initialize to 5 right here. We know that this is going to be the letter M, and we can also convert it to a character to make sure that we're aware of that. So we'll go ahead and label that as M. We're going to first, let's move this over here so we can hopefully follow along in the decompiler over here. So remember, we're going to be calling printf for all of these operations. So the way the assembly works here might look a little strange. We're going to take our first parameter, which is x. Let's go ahead and actually rename these appropriately. Oops, that's not a rename, that's a comment. Let me try that again. Let's call this x. Let's call this one y. We're going to take x and y, we're going to add them together. So we move x into edx, y into eax, add them together, move the result into local 20. So note that that is going to be passed into printf. So that's again another local variable dedicated to parameter. So let's go ahead and call this param. It'll be 4 actually, because the first parameter is this string, the second is x, the third is y, and then this will be the fourth. And I'll keep using the PAR format there. That means that this, which is simply the value of y, is going to be parameter 3. This is going to be parameter 2. Oops, parameter 2. And then of course we already renamed parameter 1. And with those relabeled, I want to take a moment here to recognize that you are doing an amazing job of keeping up. We're moving through this program pretty quickly, and you're reading this assembly language. I want you to take a moment to realize that you are fluently reading, hopefully fluently, reading through this assembly language with me and doing a great job of it. So I just wanted to pause there and note that you'll notice we're flying by here. Again, we do have a home field advantage that we know the high level code. We kind of know what's going on. You usually won't have that advantage, but hey, hopefully you're in a much better spot of reading through assembly than you were when you started the video. All right, just wanted to give you some kudos real quick. Again, nothing new here. We call printf. Next, we do subtraction. We already know that's a single instruction. Nothing super complex there. It's going to be once we get to multiplication that things really start getting a little odd. Now we have the imul instruction, which I didn't have the table, I don't believe at least. So I'm glad I took a look at this because I realized I left out the operands for the register part of these commands, and I also failed to mention that there are two sets of multiplication and division instructions. There's mul div and then imul and then idiv. And the difference between them is that the ones with the i's, with the prefix I, are signed multiplication and division, whereas the mul and div without the I is unsigned. Signed meaning that we take into account negative and positive numbers. So I'll make a quick note and update here to say that imul and idiv are signed operations. Perfect. We'll go ahead and save that.
I'll write it and we'll do it live.
All right, so back in our code, signed multiplication is pretty straightforward in this case. We multiply them together, we printf. Where things start to get a little crazy is when we start doing signed division right here. So we see that instead of just a divide instruction here, we have a CDQ, which we haven't gone over yet, and then a signed division. CDQ is convert double to quad word, which might sound a little confusing. What does that mean? It means that we're going to take the value of EAX and sign extend it, as it's called, into EDX. Let's hop over to the debugger to kind of talk about what that means. So in the debugger, we know that we're about to divide x by y, so 5 by 7. The reason we do this CDQ or convert double to quad word is for division operations, we're actually going to be using the value across both EDX and EAX registers as the dividend, and that's to make sure we avoid any overflows that may result from the division. What that means is that if my number in EAX is positive, which 5 is, that means that this most significant bit here is going to be 0. That indicates that this value is positive. And in that case, when we sign extend over to EDX, all of that is going to be filled with zeros because we want that sign to be preserved across EDX. If, on the other hand, this was -5 or another negative number, this most significant bit over here would be set to 1, and then we would see F's all across EDX here. So F's being all ones across EDX. It might be helpful if we pull the calculator back up. Let's say our value was 8,000,000,005. So that's a negative number because this most significant bit is set. It's quite a large negative number, 2 million, whatever that is. But if this was in EAX at the time we do the CDQ, that sign is going to be extended so that EDX gets all F's, and that makes sure that the sign is preserved across the entire register there. Again, if it's just 5, then that most significant bit is going to be 0, and EDX will just get 0. A little bit of a confusing concept. Hopefully that clears it up a little bit, and I think what will help even more is watching what happens right now when we step through. We see nothing much has changed because EDX gets set to all zeros, which it already was. But let's go back and do this again, but this time I'm going to modify it so that we make the most significant bit 1, therefore making this a negative number. We'll step through, and now EDX should be set to all F's, which we see right there. And again, once we actually do the division, if you remember, actually let me go ahead and do the division with the positive numbers because it'll be a lot easier to read. So when we divide 5 by 7, we'll see the quotient gets stored in EAX and the remainder gets stored in EDX, just as we said right here. Result in EAX, remainder in EDX. Hopefully that clears up a little bit of what we were saying in the disassembly window here. And perhaps I should add CDQ to our chart here. I might do that as a little subnote here for the division row. So once that division is taken care of, we move the quotient, which is in EAX, into the parameter, and we print that. And you'll notice in the next line, we do the modulo operation, which should get the remainder. And you'll notice in the assembly, everything is nearly exactly the same, except instead of moving EAX into parameter 4 right away, we take the value in EDX and move it to EAX first. So remember, remainder is in EDX. We have to move that into EAX before we move it to that parameter right there. So if you made it through division and modulo and you're still feeling good, the rest of this should be pretty simple to follow along with. The next thing we do are the shift operations. We take A, which is 3, we shift it to the left by 2. That should give us 12. And actually, if you look over here, it's funny because the decompilers, instead of putting the variable name A and then A shifted by 2, it's already filled in the values there, even though the disassembly view doesn't show that. So that's a little interesting. And then let's move down to where we're referencing our global value. And you'll see that Ghidra has successfully labeled our global value here. Again, remember this sits in the data section since we defined it. It's a static global variable. And again, pretty straightforward. We move it into EAX. We do a shift to the right by 1. And then we move the result into EDX, move the global value into EAX, move those into parameters, and print everything off. You may have also noticed that whereas shift left use SHL, shift right use SAR as opposed to SHR here. And the reason for that is SAR will preserve the sign of the register here, whereas SHR will not preserve the sign bit. So there's a subtle difference there, and I'll try to update the drawing here to reflect that there's also some variations of these commands as well. All right, so with that in mind, the next thing we do is the character shift, which again, the decompilers actually already evaluated this for us. So M gets shifted to 872 decimal, which we talked about is then divided by 256, which gives us H. It doesn't show up as you can actually convert it to H there, but what's interesting is if I hover over it, you can see that it does recognize that the character, if you look at that character array value at the bottom of that tooltip there, it does recognize it as the character H there. I don't know if there's a way to convert it to H. It doesn't much matter because we know that's what it's going to end up as. Now, the one thing you may notice a little different here is an interesting thing the compiler did for us is instead of actually doing a shift by 3, it just did the equivalent multiplication. So it multiplied EAX, which has M in it, by 8, and then added 0, and then put that in EDX. So it kind of did a little bit of maybe optimization there to avoid doing a shift and instead used load effective address. If you look at math, it checks out. If we have, let's say, what is the value of m again? It's something like 109. So if we take 109, we shift it by 3, we get 848. If we take 109 and we multiply it by 8 rather, we get 848. So the difference is negligible because we end up with the same result, but it is a little interesting to see that a instruction was replaced there from shift. All right, after we shift M, we have some pretty straightforward bitwise operations. So we take B, which is again an integer pointer, with the value, or I should say pointing to the value of 5. So first we take the pointer itself, we put that into EAX. Then we use the bracket notation with move here to get the value at that address and then push that into EAX. So again, this is 5, moving that into EAX. Bitwise AND it with 2, move the result into EDX, move the value pointed to by B into EAX right here, and then print both of those. Same thing right here for the OR operation. Nothing really crazy here. So things start to get tricky again once we get down to the comparisons. And if you remember, the first comparison we do is A plus 2 equivalent to B, or the value pointed to by B. Since the value of B, or the value pointed to by B, is 5, A is 3, this should be true because 3 plus 2 is equivalent to 5. So we can see that reflected in the assembly. We move A into EAX, we add 2 to that value, and then load that into EDX. Then we get the value pointed to by B, put that in EAX, compare the two. This is one instruction we have not talked about yet, which is set Z. All this means is set the operand, in this case AL, to the value of the 0 flag. Meaning that if this comparison comes back as 0, remember that comparison is basically a subtraction. So if these are equivalent, it's going to come back as 0. A is going to get, or I should say AL is going to get the value of 1 because the 0 flag will be set. One more time through there because the kind of double negation there makes it a little difficult to understand. Comparing two equivalent values is going to result in 0. When the result is 0, the 0 flag is going to be set. And because the 0 flag is set to 1, the value of AL is going to get the value of 1. So that'll tell us that these two are equivalent. We basically just take that value, 0 extend it into EDX, and then use that as our parameter that we print down here. Same kind of thing when we do the second comparison, which is A equivalent to B, except this time that comparison is, of course, not going to be 0. It's going to be whatever the subtraction is. And so this will be 0 set to AL, and we'll print that as well. Not too difficult to follow along with. What's the last one we do? It is a less than or equal to. So the only thing that's going to change there, if we go back to Ghidra here, is instead of a set Z, we're going to use the set less than or equal to. And you can imagine that works exactly the same way. It just looks to see if they're less than or equal to and stores that result in AL. With that, the last thing we do is we call free on B. And again, that's just to make sure that we free up that dynamically allocated memory. We then set it to null, which we see reflected right here. We move 0 into B. And then the last thing we do is return y minus x, which is as easy as doing a move EAX, y, subtract EAX, x. And since we're already storing the return value in EAX, we've already done the operations right there, so the return value is going to be already stored in the EAX register. We do the leave, we do the return, and we're going to go back to, there we go, main. So we take the return value from QuickMaths, we put that into the parameter variable right here, and then we print that result just as we specified in our code. All right, that's one function down. I know it's been a lot, but let's keep going to loops. In case you forgot, here's the high-level code for loop soup. This might be a fun one to use the Ghidra graph view for. So we set x equivalent to 1, check if it's less than 3, then we run a couple loops here to modify x's value. And then at the end here, we have an infinite loop where we break once x is equivalent to 17, and that's it. So with that in mind, let's go ahead and pop open function graph, which will hopefully help us dissect some of these loops here. So again, at the very top, nothing too special going on. We print the function header, and then we get right into assigning the value of x. Let's go ahead and rename this to x, so we're tracking that. And then we jump down to here. We compare x to 2. If it's less than or equal to 2, we're going to keep moving through the loop where we simply add 1 to x, and then we check this, or we print out the value of x right here. So this is going to be a parameter value. Well, oops, we'll go ahead and label that as such. Label this as par1. Label this as, or I'm sorry, that should have been par2. And then this will be par1. Oops. There we go. Perfect. And we'll just print out the value of x each time we increment it. So once we are no longer less than or equal to 2, meaning we are equivalent to 3, we move on. We then reset x to 0. Again, that's right here in the for loop. We reset the value of x to 0. And it's a very similar loop. We just compare with 10 this time, print out the value. Nothing much has changed there. The only little weird thing you'll see here is that since we go from a loop right into another loop, you see this kind of self-referencing loop right here. So once we get through the first loop, if you remember, at the end of this, x is going to be 11. So when we get down here, we're going to go ahead and run through the do while loop, which the first thing we do there is increment x and then print the increment value of x right there. And then we compare to 15 right here. I'm going to just show you the conversion, or 14, I should say. 14 right here. If it's less than or equal to, we keep going. You get the idea. So next is going to be a little bit different because we're going to start a infinite loop that starts right here. And then we add 1 to x. We compare it to hex 11, which is, oops, whoa. Let's slow down here. That is going to be in decimal 17. And as long as it's not 17, we're going to loop through this, which is basically a NOP, and then a jump back to the start of the loop. So that's what an infinite loop looks like in assembly right there. Just a quick no operation, jump right back to the start of the loop. As soon as it does equate to 17 though, we're going to jump down to here, and then simply put x is 17 now, print out our statement. And then the last part of the function is pretty straightforward. We jump down here, we do a NOP, a leave, and a return. So loop soup, fairly simple, much simpler than the quick maths function to walk through. All right, next up in main is terms and conditions. And if you remember, this is working with a lot of conditional statements and Boolean values. So let's head to our assembly here. We already know the prologue by this point. Let's go ahead and relabel some of these. So we start out by having A equivalent to true and B equivalent to false. So let's make sure we label those accordingly. This is going to be A. This is going to be B. Oops. Again, I keep hitting the semicolon button, I think, instead of the L, which takes me to comment. There we go. Now, the thing that's going to look a little weird here is this ternary operator. So we select the string we print based on the value of A, whether it's true or false. In assembly, what that's going to look like is we're going to take A and compare it to 0. So we're basically taking A and seeing if it's false. If it is false, we're going to jump down here, and we're going to move that string false into our parameter value and print that. Let's go ahead and label these as our parameter values again. There we go. But if A is not false, we're going to load what's at this address, which again, Ghidra just has interpreted this not as a string, but we can convert it to a string by going to data and string. And that should fix that when back in our listing here. In fact, let's go ahead and open up the function graph for this one as well. It'll be good once we get down to the conditionals. As you can see down here, it's going to get a little crazy, but it'll be cool to visualize that. Hopefully a little easier to follow along. All right, I've extended those out a little bit so we can see a little easier. Here's the first comparison we made with A. Let's move down here. The next comparison is after we set A equivalent to B, we say, oh, A is actually false now. Then we set it back to true and we say, hey, it's true again. So let's see what that looks like. You can see right here, we set the value of B, or we put the value of B in EAX, and then we move it into A. Since B is a single bit, we simply take AL and move that into A, and then we compare to 0. And depending on that is what we print, either true or false. All right, so after those initial equivalency checks, this part gets a little more tricky once we get into the logical and OR. So unlike bitwise and OR, this is not going to be a simple instruction to just AND these two together. Instead, what's going to happen is we're going to check to see for the AND operation if A is true and B is true. And in C, how this works is if the leftmost operand in an AND operation is false, we know that no matter what, this is going to equate to false. So it won't even look at B. It'll just be like, hey, A is false, so go ahead and just print false because we know this is going to be false. With OR, if either one of these is true, so if A is true right here, it's not even going to look at B. It's going to say, hey, A we know is true, so go ahead and print true. And I say that because we're going to see that reflected a little bit oddly in the assembly here. So for example, we move, let's make sure we're in the right spot here. So the last thing we do is we say, hey, A is true. We do the print there. Okay, we're down here. So after the last print for A being set to true, we say, okay, compare A to 0, meaning compare A and see if it's false. If it is indeed false, we don't even go through this check of B, we go right to printing false. Just like I said, if the leftmost operand is already false, we know that this can never be true, so we just move right here. On the other hand, if this is true, then we go ahead and check B, and then if B is false, we move to printing false, otherwise we print true right there. Same thing with logical OR, except this time we're going to jump if A is not equivalent to 0 after the comparison, because that means it is indeed true and not false. So if A is true, we go ahead and print true. Otherwise, we check B. And if A or B are true, we print true. Otherwise, if both are false, we print false. Lots of lovely logic games we're playing here. So here's where we start worrying about that order of operations bug, if you will, that I was talking about earlier in C. And that is if you do a bitwise AND between C and D and then equivalency, it's actually going to evaluate D not equal to 0 and then bitwise AND that with C. So let's check out the assembly for that. Right here, this is going to be C. This is going to be D. So we compare D to 0, which again, we're doing that equivalence first, which is probably not what we wanted. And then we bitwise AND that with C, and then we test the value of that, and that decides whether we print true or false. Whereas really what we wanted to do is AND them first and then compare to 0. So in our assembly, we'll see that we do right. Oh, I don't know why I'm looking for it. It's literally right below this line here. So it's just 3 quick instructions. We move C into EAX, we AND it with D, and then we test, which again, that's the equivalent of a bitwise AND, and we set the value based on that. So after we get through those bitwise operations, we now get down to the if statements and nested if statements, which usually are pretty straightforward. It can get a little dicey to read them in assembly if there's a lot of nesting going on, so we'll see how that looks. First comparison is just checking to see if A is true, then we check if B is false, or we check if B is true, and our print statements will adjust there. So let's get those through those 3 first, and then we'll get to the nested statement down there. So the first one that checks if A is true is pretty straightforward. We compare A to 0 or false, and if it's false, we skip right ahead. We don't do the print that says A is true. The next one is checking if b is false. So this does something a little bit interesting, how the compiler has rendered it here. We move b into EAX, we XOR it with 1. Remember that exclusive OR means that if either of these values is 1, then it will return 1. If both of them are 1 or if both of them are 0, it will return 0. So if b is false and we do this XOR, it will set EAX to 1, and that will put us right down to, let's see, set EAX to 1 if b is false. Logic, big brain time. If EAX is 1, or if AL is 1 here, this will be not 0. So we'll move down here and we'll see the string. If you see this, b is false. So that's what we would expect. If it's not false, what's going to happen is this is going to be 1. We XOR it with 1, AL will be 0, and we'll skip right ahead to the print statement that says, if you see this, b is true. That was one of those cases where with this nesting and the if-else, things can get a little tricky to evaluate. Speaking of, this next one is a true nested if statement with an if followed by an if-else. So first, we check to see if A is true. If it is true, we check to see if B is false, and then we print accordingly. So let's see what that looks like. So if A is false, we don't even move to the side, but if it is true, we move over here. We check again to see if B is false, and then we print accordingly. Not too bad, really, now that we understand that kind of flow here. So let's see what's next here. We then say if A not equivalent to B, so that should be a quick comparison. We have already seen plenty of those, so nothing too scary there. Let's go back here. The next part and the final part of this function is the switch statement. So we set x equivalent to 2, and then we evaluate what to do based on that value of x. Let's get back into Ghidra, right? Oops, I want to go back to the graph view actually. Here we go. So let's see, this is all of our A and B operations. We should be right down here. So this is x. Let's go ahead and rename it as such. We move the value of 2 into x. We compare it to 4 first. So let's take a look back here. So right here, if x is 4, we should do a subtraction of 2 and then break. And so we see that's exactly what happens right here. On the other hand, we compare, if this doesn't equate to 4, then we move down to here. We compare x with 4 again, and if it's greater than 4, we go to the default case down here, which is print you never should have come here. And that occurs, let's see, right down here. So this switch statement can really make your assembly look really wonky. And sometimes you'll have a switch statement that has so many cases that you'll see what's called a jump table. And that looks something like, let me find a good graphic of a jump table here. Here's a good example from reverse engineering Stack Exchange. If your jump statement, or if your switch statement has several different options beyond, I think it's maybe 8 or 9, don't quote me on that, but after a certain number of cases that you've defined, you'll start seeing, instead of these various branches that we see in our disassembly to account for every case, you'll see what's called a jump table. So basically you take the value, like x here, and you perform a jump based on what offset is in the table, the jump table at that location. And all of these different offsets lead to different code blocks for what will be executed in that case. So I didn't have an example of a jump table in this one, but just so you know, you might see that represented slightly differently when you have a switch statement with a lot of different options. So you may have noticed the case for 3 looks a little odd because when we have case 3, we divide x by 2 and store the result back in x. This shift right that you see here by hex 1f is another sign extension function similar to the one that we saw earlier with CDQ. We're basically just sign extending into EDX there, in case you were wondering what that was about. And then this shift right here by 1 is the same thing as saying divide a value by 2. Anytime you shift by just 1 byte to the right, you're dividing a value by 2. Anytime you shift to the left, you're multiplying by 2. So that's what that is about. Everything else here, let's see, if it's greater than here, we get to the never should have come here. Otherwise, we compare to 1. And what was case 1? Just add 1 and then multiply by 2. So not too much that's surprising here. Here's that example of shifting to the left by 1 to multiply by 2. So again, depending on how many cases your switch statement has, it can be really messy to look at in assembly. The function graph view here really helps out with navigating through if statements and switch statements like this, because if we're just looking at the raw assembly, it can sometimes get kind of difficult to tell what branches to where. And I will say the decompiler view does help a little bit with that. Although I am noticing that Ghidra failed to notice that that was a switch statement at all. Kind of embarrassing, Ghidra. All right, so with that, we are now in our function disarray, where we, if you remember, we made that 10 integer array in main. We pass that in, as well as the size of that array. We print the function header. We create a local array doing the exact same thing we did in main, where we set the values to 1 through 10. We check to see if the passed in array size is equivalent to our local array size. If it is, we compare them and we print that they are equivalent as long as they are equivalent, which all of them should be. So let's get through that piece before we go any further. All right, so I'm going to stay in the function graph for now. And you can see I've already relabeled a lot of the variable names here. So again, we print the function header, then we initialize I for our for loop, where we're going to initialize that array. This is the exact same loop we saw in the main function, where we go ahead and set the numbers 1 through 10 into that array, which should be, let's see, passing in EAX. Yep, that should be this guy right here. So I'll go ahead and label that as our local array. So once we set up that array, what we're going to do is compare the sizes. So again, the array size was just a macro that equates to 10. You can convert this to decimal to make it a little easier to read. And we're checking the second parameter, which was our passed in array size, and seeing if it's 10. If it is 10, then we'll move over here, where we'll set up our second for loop, where we'll set j equal to 0. We'll walk through both arrays here in this loop right here. Again, noting this notation here to walk through and access each of these separate arrays, and we'll compare their values right here. Oops, I just realized I mislabeled this. This is not our array value because we don't define that. This is just parameter 3. So let's fix that. Get back down here. And again, there's nothing too special here. We access the arrays, we see if they're equivalent. We print out if they are equivalent each time. All right, so after those array comparisons, we get down to where we allocate our dynamic array and then try to reallocate it to double its size. I've gone ahead and labeled everything here. Pretty straightforward right here. We ask for, again, an array of 10 integers of 4 bytes each. So we're asking malloc for 40 bytes of memory on the heap. We get the result from malloc. We move that into dynamic array. Oops, didn't mean to double click that. If it's null, we will go ahead and print that and then we exit. But if it is not null, then dynamic array now holds the address in the heap where we can start storing all of our integers. So let's move down past where we check if a dynamic array is null, and then we quickly print out that, hey, dynamic array has a size of 10 right here. And then we start the reallocation process. So we are now asking for an array size of 20 integers, 4 bytes each. That's 80 bytes. Once again, we call realloc with that number in mind. And assuming that that is successful, we store the result in temp array and we check to see if it's null here. If temp array is not null, then we move down to right here where we move it into EAX and then move it into dynamic array and then print that it has a size of 20. We can convert that hex to, oh, did I not click on the right thing? There we go. Convert this to decimal, and we see that, hey, it's now size 20. And then the last thing we do is we move dynamic array into EAX and free it, and then set it to null, as we see in the high-level code right here. So that's it for disarray. Moving right along to disappointers. All right, for disappointers, if you remember, we pass in our string, which is I'm a string, look at me, as well as the string size. We make a local pointer and set it to string, and then we basically traverse that string and print out each character, set it to null, change the last character from an exclamation point to a question mark, and then print that, and that's about it. So going back to assembly, right here we get the value of our string that we pass in. So let's go ahead and actually rename that to, that's one I didn't rename, string. And then the second parameter is going to be string size. So go ahead and rename those real quick. So we take the value of string, we place it in a string pointer, and then we place this string here, which is simply the %C, a format string. Let's go ahead and set that to a string just so it renders a little nicer. Or I'm sorry, that's not the %C, that's right below here. Go ahead and define that as well. This was the tab. This is a \t, which is our tab that we print right here. That's all that's going on there. So we print the tab, then we jump down to here. So we take string pointer, move it to EAX, get the value pointed to by string pointer, which is the first character of our character array. And then we test to see if it's null. If it is not null, it will go back up to this loop where it will take the string pointer and then print out the character at that location right here. And then we add 1 to our string pointer, which again, remember that that is pointer arithmetic. So we're really adding 4 bytes to there to get to the next character in that array. You can see that reflected right here in our for loop. So once we get done with that loop, let's see here, we get through here, get down to here, and this is where we're starting to set the value that is currently an exclamation point, which is 2 off of the end of that string. We're setting it to a question mark. So what does that look like? Well, this hex 3f here, if we go to convert, is our question mark. So we basically take, let's see right here, we take the string, we add edx, which is our string size -2, and then we use that as an index. We get the value at that index and we set it to the question mark. We move that into EAX, we move that into our parameter, and we simply print it right here. This one's pretty straightforward. Just wanted to give you an idea of what the pointer operations look like. But at this point, we've seen plenty of array operations that kind of show us the same exact thing. So let's go ahead and move on to the next one, which is struct your stuff. All right, so in struct your stuff, we're not passing anything in. We simply use our custom thing struct, which is made up of a character, a integer, and a pointer to an integer. Define 2 of them, set up their C and X's, and then if you remember, we point thing.px to thing.x's address, and we also point thing2's pointer to that same value's address, that same value's address there, so that when we set thing.x to 12, we should see the same value 12 for both of these. But here's where things get a little complicated when we move to the disassembly view. Ghidra doesn't know that that custom structure exists. But as a human reverser, there are some hints that we'll see that can tip you off that a custom structure is being used. And not in this function, but later on I'll show you how to define one of those custom structures when we do our linked list function so that Ghidra can better understand and display those structs. For now, let's try to reason through this just on our own. So before we label the first set of local variables here, let's just trace through this code. We're going to move x into this local variable. Okay, good so far. I'm going to move 13 in this other local variable. Good so far. That's the equivalent of setting these 2 right here. Where it gets a little confusing is the next instruction takes the address of local 18, then we add 4 to that, and then we move that address into local 10. Let's back up and think about what's going on here. And in fact, let's go ahead and label these. We're cheating a little bit because we know how the structure look and what the names of these things are, but I'm doing so to prove a point for right now. There we go. thing.px. There we go. So we're taking the address of thing C, which is our character. We add 4 to it. Knowing that a character is 4 bytes, that essentially means that we're taking the address of thing C, adding 4 bytes, which will bring us to thing X. We then take that address and move it into thing.px. So this looks really odd in assembly, right? Why would we do this kind of circular referencing of local variable addresses? Well, when you see something like that, that can tip you off as a reverser that a struct might be used in this function. And you may not know that for sure, but I'll show you again later that you can define custom structs and play around with them. So let's go ahead and move on. We know now that this is going to be thing2C. This is going to be thing2X. And so down here, this is going to be our thing to px, and notice we follow the exact same procedure. We take the address of thing C right here, we add 4, and we store that in thing to px. Then we set the value of thing x to 12, and finally we print that both as both as a dereferencing of thing2.x, we don't print thing x, we print thing 2x, and then we print the dereference thing2.px, and I'll fix that typo. I should have a asterisk here to indicate that we're dereferencing that pointer before printing it. But the long story short of that is if we go here and run our practice program again, and Defender will complain, there we go. We should see thing2.x is 7, whereas thing2.px dereferenced is 12 because it's pointing to thing.x right there. So again, it can be a little tricky to work with custom structs as you're reversing, but there will be some telltale signs such as that cyclical referring to local variable addresses or other addresses that you may see as a human reverser that might tip you off. And from there, you can either define a custom data type, which I'll show you how to do in just a moment, or you can go through what we just did, or like we just did here, and just relabel everything so that you know you're working with a struct. The time has come where we are finally at our final function to go through an assembly. We went through linked list, not to be confused with Zelda list earlier when we went through our high-level C program. And again, all we're doing is building a very simple linked list using a custom node struct here. We're setting the values or inserting some values into that linked list, printing it out, and then freeing it up and deleting those nodes one by one. So let's head over to the assembly and see what that looks like, and also talk about defining custom structs. All right, so I've gone ahead and labeled some things here and converted the numbers to make them a little easier to see. If you remember, the first thing we do is declare head, which is a new node, and set it to a node pointer, I should say, and set it to null, which is right here. We then load in 99 and the pointer head, and we pass that to insert at start of linked list. So let's go ahead and go into this function, and we'll go ahead and pull that up here as well. So first thing we do is call malloc, good old malloc again, with the size of node. Well, if you go up to the definition of node, it's got an integer, which is 4 bytes, and then a node pointer, which is another 4 bytes, for a total of 8 bytes. Let's scroll back down here just to make sure we're able to follow along. And so we request from malloc 8 total bytes. It's kind of a redundant conversion I just did, but you can see it's 8 bytes we're requesting. We then compare the result of that to null, which is this check right here. So let's go ahead and label this as new node, and we'll call just this param1. Oops, param1. And as long as new node is not null, we move down here. We get a new node. We put that into EAX. We take the param2, which is the data we want to insert into our new node. Let's go ahead and rename that data. Then we take that data and we take the address to new node and set that to the value of data. The next thing we do is take head, the reference or the pointer to a node that we passed in, and we set that to new node arrow next. So let's go ahead and rename this to head. And then we take that head pointer, place it in EDX, and then we move it to EAX plus 4. So that is basically new node data plus 4. Since data is an integer, we're skipping over this 4 bytes again. And once again, this is another telltale sign that you might be working with a custom struct, because we're doing some weird offset with a scalar from a register, just like we saw earlier doing offsets from other local variables in the function. But in this case, we can actually, so if we're able to deduce, in this case, what our struct looks like as a reverser, which is pretty simple to do in this case, we can actually go down here to the data type manager. Let's click on this arrow and let's go to, or actually let's right click practice.exe and go to new structure. And from here, we know our node structure, we'll call it node, has a size of 8 in total. So that's 4 bytes for the data, which is an integer. We'll go ahead and define that as int, and it will automatically adjust this struct for us as we go through here. And the next one is a node pointer. But wait, we don't know what a node is yet. So let's just leave that as a pointer for right now. And we'll go ahead and save that. To create our node pointer, what we can do is take our newly defined node object by filtering it here, right click, and put, let's see, new pointer to node. So now that we've defined node, we can go click back into node, and now that we've established that a new pointer to node, we can use node pointer, and everything will work as intended. So you can see our struct defined right here. Let's go ahead and save that. So we know that the first parameter being passed into this function we're looking at right here is going to be a node pointer. So let's go ahead and set head to the type node pointer. We can do that by right clicking, set data type, and then we'll choose data type, node pointer. We'll do the same thing with new node. We'll set the data type to a node pointer. So now that we've defined this as node pointers, we also need to go over here to the decompiler and set this to a node pointer as well. We'll retype the variable to node pointer. And Ghidra will actually now start referencing those fields as we would expect to see them. Now you'll notice that it doesn't have the labels quite right, and I think that's because, let me make sure, yep, I didn't go in and name these. So let's go ahead and name this data and head, or next, excuse me. And we'll save that. And now Ghidra has fully converted this to the structure data as we would like to see it here. And you can see that also reflected in the disassembly window. Pretty cool. So now that we've done that, let's go back to linked list. And now we need to do the same thing in this function. So we know that in our linked list function, head is going to be a node pointer, and then this one down here, to delete, is also going to be a node pointer. So let's go ahead and set pu var, or let's see, there we go. I had to redefine or retype a few of those to make sure they were all node pointers. And now this looks somewhat more similar to our high-level C code and makes it a little bit easier to read and understand what's going on in this function, which let's go ahead and do that now that we spent so much time trying to define out our little custom struct there. We can finally get to the meat of this, which is looking at this linked list function here. So with all those definitions done, this should actually be quite a bit easier to read through. We know that we're going to move 0 into head just to make it null to start with right here. And then we'll have 3 calls to insert at start of linked list with 3 different numbers. Each of those will be reassigned back to head. Then we'll put the value of head into current. And while current is not null, we'll print the data in current and push it to its next node in the linked list, and then print n. So let's get through that section first before we wrap up this one. So we send 99 and head over to insert at start of linked list. And then we get the value from that, move that back into head, rinse and repeat 2 more times until we get to this point where, okay, sorry, I confused myself for a second. This is just the last call to insert at start of linked list with the value 33. Down here is where we move our head variable into a local variable called current right here, also a node pointer. So let's go ahead and name this current. There is some weird-ish movement going on here. You'll notice I'm not touching this variable or renaming that to current because it's being used in multiple places for multiple different purposes. So I'm going to go ahead and leave that alone, but I'm going to define this one as current instead. So we take current, we do a small print there just to get this head statement out. And then we move to a while loop where we check right here to make sure that current is not null. As long as it's not null, we'll go into our loop where we'll take current, we'll move it into this little variable here. We'll access the data of current and move that back into the same variable. And then we'll print that using printf. So again, I don't want to label these because this is being used in multiple places for multiple different operations. And if I called this current or current2 or whatever, it would probably get really confusing. So I'll just leave that variable name alone and just accept that it's going to be a little bit confusing and not a lot of bit confusing as we work through this. So we print the current TAC data. And then after that, we update, we move the value of current into this pu var1. We take pu var1.next and move that also into pu var1. And then we finally move pu var1 back into current. What that looks like in our high level code is this piece right here, getting current.next and moving that back into current. The compiler has just used a bunch of other local variables to accomplish the same thing. So once our loop is over, we print end, and then we move on to actually destroying this whole linked list. So we set current back equal to the value of head. We make a new local variable called toDelete, set it to none, and then we basically iterate through current, setting toDelete to that. Oh, wait, I just realized I have defined this 2 times. That is such a shame. I'm going to have to fix that. That's probably what's messing up the compiler too, is I've defined 2 separate variables there. So by taking off that definition, I should now be referring to the same one. I'll make sure I go through right now and recompile that real quick. 1 second. Really glad we found that. It won't change the executable too much, but I did update it so that you all will have the correct executable and not redefine that. So again, we're just going through, we're going to basically iterate through the linked list. We're going to set current or set toDelete to the value of current, then set current to the value of current.next, and then free up toDelete and set it to null. Basically just getting rid of each node one by one until current is finally null, which means we've reached the end of the list. So let's hop back to Ghidra, see how that works out. So we are, let's see, right after the printf to end here, we move head into pu var1, we move pu var1 to current, and then we move 0 into local 18. That's going to be our toDelete right there. And then we jump into our loop, make sure current's not null. As long as it's not null, we'll go up here. We'll move current into this temporary variable into local 1c. And again, the reason it's doing this local 1c is this is actually still toDelete, but I redefined it. So whoopsies. Sorry about that. In your assembly, if you look through the assembly that's going to be posted in the GitHub repo, it'll actually be the same variable that we see up here, toDelete. But because I redefined it like that, it's going to say this is a whole different variable. Anyway, we get current, we move it into pu var1, we get pu var1.next, we move that back into pu var1, put it back all the way to current there. So we then take toDelete, move it into pu var1, toDelete.data, pu var1, and then pu var1 into local 28. So that's just passing it over to printf there. That's all that's doing is this piece right here, taking toDelete.data, printing it, And then the next thing we should see is a call to free, passing in to delete to free up that memory, and then setting this to null here. I guess I'll relabel this as also to delete to shorten it, just so we can see the operand there. So again, once that loop is done, we have a couple of nops, a leave, a return to main, which is right here conveniently. And once we get through linked list, we move all done into our printf, our final call to printf. And my friends, that has taken us through this entire assembly journey with one epilogue, I should note, and that is the 64-bit version, which I talked about a little earlier. So real quick, I won't spend a whole lot of time on this because we've already spent so much time together today. I want to show you what happens when we compile this for 64-bit on Windows, and just a quick look at how that changes things. And I already have it loaded up here, although I do need to import the new version of that file here. Go ahead and pop it open, let it analyze. All right, so we're analyzed here. You'll notice right away that the craziest thing about this x64 or the 64-bit executable from Visual Studio is that when we go to main, all of our functions have been collapsed into one giant main function. And I'm sure there are some options you could tweak with Visual Studio to avoid doing this, but I just think it was funny that it just basically took all the code in our file, put it into one giant function instead of having to deal with a bunch of different function calls, which is, to be fair, probably pretty efficient. The other thing I wanted to point out is that you'll notice that the 64-bit executable from Visual Studio uses the fast call calling convention. And if you remember, that means that the first few arguments are going to be pushed to registers, commonly RCX or RDX or ECX and EDX, and everything else is pushed right to left, and the calling function cleans up. So you can see when we pass in our argc, argv, etc., instead of being stored on the stack, they are stored in RCX, RDX, R8, which is one of those 64-bit general purpose registers, R9. And you can move through here. I'll leave it as kind of a exercise to work through on your own, to look through the 64-bit version of this and see, besides this compilation of all of our code into one main function, what other differences exist between the 64-bit version and the 32-bit version we looked at in Ghidra just a moment ago. Other than that, those are really the only things I wanted to point out to you, are the use of the 64-bit registers and the fast call calling convention. Again, I'll leave it up to you how far you want to delve into the 64-bit version. But if you do have questions for me, please let me know. But wait, before we part ways, I do want to issue you a final challenge that will test everything that we've sat down and gone through here today. Except this time, you won't be going through a program you wrote, you'll be going through a program that I wrote, and you won't have access to the high-level C code like we did here, and that's all part of the challenge. What I've done is I've added to the GitHub repo for this video what's traditionally called a CrackMe challenge, which is basically a executable file that you don't get the source code to. You load it up into your disassembler and your debugger, you run it, you can play around with it and throw whatever you want at it. The goal is to find a hidden flag in that program, and you can find it through applying all the reverse engineering and assembly language reading and parsing techniques that we worked on today. In the description for this video, you'll get a link to this form. If you choose to take on the challenge, you can submit your name, the flag, and then a quick CAPTCHA question just to prevent some spam. And if you're successful in finding the correct flag, your name will be forever immortalized in the GitHub repo for this video. So hopefully you enjoy this fun little challenge to test your knowledge. And if you do like it, please let me know so that we can preserve that for future videos. It's the first time I'm doing something like this. I'm a little afraid someone's going to abuse this form. I'm going to try to keep it as secure and locked down as I can. But if things do get abusive, I may lock down the wall of fame after that point in time. But I'm going to do everything I can in my power to make sure we protect it, because I do like the idea, and it's a great way for all of you to be recognized for the time you put in to learn this stuff. With that said, I've given you all of the knowledge I can in this moment to demystify x86 assembly. We wrote our own C program. We went through it in Ghidra. We saw it in a debugger. We went through that cheat sheet and we discovered everything. Well, not everything. All of the foundational things there are to know about x86 assembly and all the basics you need to get started in reversing. My name is Jeff of All Trades. I've loved sharing this journey with you. I can't wait to hear your feedback. Please let me know what you'd like to see in future videos in this series. If there's any questions you have, and like I said, keep an eye on any edits or additions in the description and pinned comment for this video. Until next time, keep on learning, keep on sharing, keep on being good to each other. Goodbye.